The next part of our conversation is this idea of infinite limits. And so I've got this graph. To get us started, I invite you to take a moment, maybe pause, copy that graph. So what I've got, here's my XY plane, and I've got a vertical asymptote happening there at 2. And then you see the nature of the function, right? It's got this kind of behavior on either side. It's also got a horizontal asymptote at the x-axis. That's not so important for what we're going to discuss. It's really that vertical asymptote. Okay. So infinite limits, what does that mean? Well, look, it's shooting off to infinity, right? This direction. Shooting down to negative infinity, this direction. Okay. So what if we were to ask this? Part A, hey, what is the limit of this function f of x as x approaches 2? You think, well, at 2, this is a two-sided limit, right? So the left side and the right side have to agree. Well, on the left, it's shooting up to infinity. On the right, it's shooting down to negative infinity. Well, those aren't the same thing. So this does not exist. And that's our answer, right? The left and the right sides don't do the same thing. But what if we were to say, hey, let's take the one-sided limits then. And now this is similar to things we've done, but definitely a different, the details are a lot different with that vertical asymptote. Okay, the limit of f of x as x approaches 2 from the left, from the negative side. Okay, so if I'm on the left side of 2, the y value is going up and up and up to infinity. It never stops. So this answer, we say that is equal to infinity. We do have an answer. The real purists in math would say you can never equal infinity. Infinity is not actually a number, it's a concept. And you can't equal infinity because infinity goes on. That's the whole idea. And they make a great point. But we're going to say it anyway, just because that's how we're going to think of, right? So the y value's going up, we get it. The y value shoots up to infinity. So as we approach 2 from the left, the y value goes up and up and up with no bound. Okay. Well, we might as well do the right side as well. All right. You saw that coming. The limit as x approaches 2 from the right side, well, we go down, down, down. So we're going to say this equals negative infinity. And there we go, the infinite limits. Okay, well, things are always much easier when we have a graph to look at, right? We can do it visually. But what if we don't? We should probably do some of those sorts of questions together. Determine the infinite limit. Let's pull that up to the top of my screen. How about this? The limit of x plus 1 over x minus 5. X approaches 5 from the right side. Okay. Now, just like any limit problem, we would always begin by simply trying to plug in the 5. So let's try that out. If we plug in the 5, what happens? And that's my note here. Okay, let's see. Well, plugging in x equals 5, well, that would give us 6 over 0. Ooh. Okay. Something other than 0 over 0. We've got a number divided by 0. The 6 is really not important. Simply the fact that it's a number, some number other than 0 over 0. 6 over 0 tells us there's a vertical asymptote at x equals 5. Okay, 0 over 0 is a whole. Anything else over 0 is a vertical asymptote. So what are we going to do? Well, actually, this is good news. If we've got a vertical asymptote, then we know the answer to the limit is either infinity or negative infinity. There's only two options, right? I mean, go back to our last drawing. If there's a vertical asymptote, either you're shooting up to infinity or you're shooting down to negative infinity. I mean, right? That's the only two possibilities. So here's what we can do. Here's what I just said on paper. Does f of x, does the y value go to positive infinity or negative infinity? And keep in mind we're on the right side of 5. Only two possibilities. How are we going to figure it out? Looks like I ran out of space on this page. So let me do this sort of thing here. There are two options. Both are equally valid. Okay. The first option is a good one. Simply graph your function. Okay. So this sort of thing is going to be an option for you guys on tests. You know, you can use the website Desmos, DESMOS.com. If you've never used that before, very, very user-friendly. Far superior, in my opinion, to a handheld graphing calculator. Really crisp, sharp. It's not all pixelated like handheld calculators can be. And very, very, very user-friendly. Desmos.com. I'm going to do a video doing a quick just preview of Desmos. Obviously, if we were in class together, I could show you guys on the projector. That's not the case. So I plan on doing a pretty brief intro just because it's so user-friendly, and we just kind of want to graph functions. That's mostly what we want to do. So I will be doing that shortly. It may even be up by the time you guys watch this video. I may have done it already. We'll see. Here's a good option. Just graph that function, right? So if you do that, then you'll get an answer, and that's a great way to figure it out. But there is another way to do it without graphing. And that's our table. In this case, using a table is not a last resort. It's actually a really good option to do this if you are not able to view the graph. So here I've got our table. I'm just going to go ahead and do this with the table in this style for this one. So let me get this previous paper out of the way at this point. Using the table. Okay. So if you recall, we were looking at the limit as x approaches 5 from the right, x plus 1 over x minus 5. Okay. And you notice I've only got one table this time because we only need to look at the right side. So I'm going to pick values a little bit bigger than 5, right? And plug each of those in to our function. So I got my calculator here. And all right, let's do it. 5.1 plus 1 in parentheses. Don't know how well you guys can see that, divided by 5.1 minus 5 in parentheses. And that actually gave me a nice whole number of 61 when I plug in. Okay. Let's try 5.01 plus 1 divided by 5.01 minus 5. 601. Maybe you see the pattern. What's going to happen when we plug in 5.001? You might have guessed it, 6001 from our table. Okay, so let's think about this. We plugged in these numbers a little bit bigger than 5, approaching 5. And look what happened to those y values. They're getting larger and larger. Now there's only two possibilities for the answer to this limit. Does it go to infinity or does it go to negative infinity, positive or negative? And well, from this list, seems pretty clear that it's going to positive infinity, so I'll just write infinity there for positive infinity, since all of our numbers there are positive, and they're getting bigger and bigger. And that's a very valid approach for a case where you've got a vertical asymptote. Okay. By the way, you know, some students ask, I might as well just put this in the video. Some students ask, well, do we really need to do like 3 values of x? Can I just start with 5.001 and see this number and be done with it and know it's positive infinity? And I would say no, you don't want to do that. Only looking at one number does not give you an idea of how it's moving. So if you remember, calculus is all about change. How is it moving in time? If I see all 3 numbers, I see, oh, wow, from 61 to 601 to 6001, it's getting bigger really fast, right? I can picture that, you know, we're headed, 5 on the right side. So, oh, it's getting big really quick. If all I knew was this last one, that wouldn't tell me how it's in motion. So that would not be enough information, because maybe if I did another 0, maybe it would go down. Maybe it is going down, it's just really high up, but it's still falling, right? So we want to see the movement. Okay. I'll show you guys another one here. I'll get rid of my note at this point. Now this is interesting. Throw some trig in there. The limit of tangent x as x approaches pi over 2 from the left. Okay, well, we still have our 2 options, equally valid. We could graph, or we could create a table. If you know what the graph of tangent x looks like to enough detail to be able to answer this, then that would be plenty. If this was on a test or a quiz, I would want to see that graph. I can't read your mind. So don't just picture the graph in your head. You got to draw it out and let me know, that you're thinking of it. But I'm going to go ahead and actually begin with the table, and then we'll do the graph second. So, and then that'll kind of mix it up. Okay, so what would the table look like here? So pi over 2 from the left. First off, maybe I'll just kind of cover this part up. That's where I've got my graph here in a moment. The table, we need to have a decimal approximation for pi over 2. So I put that in my calculator, and this is all the decimal digits it gave me. Pi over 2 is approximately 1.570796327, and then my screen ran out of space. So here's what I thought. I'm going to make this table. I'm going to start with 1.57, and then I'm going to approach, since I'm on the left side, I can take a number a little bit smaller. Okay, so I'll just knock some of these decimal digits off, and 1.57 is less than this. Then I'll add a couple more decimal digits on there. So I'm approaching that value. And since it was a 0, I had to add on the 7, the 0.7 as well. And then to get a third one so I can see it in motion, then I added the next decimal digit, 9. And so I'm smaller than pi over 2, but I'm approaching that value. And I think that will give me enough information. You might also think, why are we doing this at all? Can't we just plug the pi over 2 in? I probably should have stated that from the beginning. Well, it turns out that will give you an error if you try to plug pi over 2 in. There is a vertical asymptote happening there. Okay, let's try this out. Tangent at 1.57. And be sure you're in radians. Everything we do in this class, by the way, is going to be in radians. If we ever use trig or plug anything in, to trig functions, it's always radians, always radians. Okay, so I got 1,255. I'll give myself maybe 2 decimal places, 0.77. Okay. And then if I go to the next one, 1.5707, get a little bit closer, 10,381.33. Okay, well, I got a pretty good idea of what's happening here. But let me do one more, just so there's no doubt. 158,000, oh yeah, 057.91. And so as I approach pi over 2, seems pretty clear to me that those numbers are getting quite big, quite fast, and they're all positive. That's going to positive infinity as I approach pi over 2 from the left. The graph, if you remember what the graph of tangent x looks like, if you recall, it passes through the origin. There are these vertical asymptotes. You may remember these occur at pi over 2, negative pi over 2 over here. So that would make this pi, and this would be 3 pi over 2. Tangent, it has a period of just that width, pi, so it turns out it does this, and then it repeats that shape again. You get the idea? So what is happening as we approach pi over 2 from the left? And you think, well, that's right up here. As I approach pi over 2 from the left, and yes, that is going to positive infinity, as opposed to if we approach from the right, we'd go to negative infinity. And that agrees with our answer from the table, positive infinity. Okay. You know what? I've got a couple more of these. Let's save those for the next video. We're already at about almost 17.5 minutes for this one. More examples similar to these last problems there on infinite limits.